Hi folks, Mr. Long here. We're going to do a quick screencast on graphical derivatives, and this is a topic that it allows you to assess a student's understanding of calculus without getting into any difficult algebra. And I really like these questions. They're great questions to see if you understand notation, to see if you understand whether a function is differentiable or not, and again, in the absence of a lot of algebra. So they're great questions. They can be used in the Ontario curriculum, in the AP curriculum, and they certainly are used in first-year university. So here we go. Let's get started. So what we have here, there's going to be three questions, and they're all going to focus on this graph. And it's a pretty funky graph, as you can see. There's a lot going on. We have some point discontinuities. We have a vertical asymptote. There's a whole bunch going on here. And so the first question is, what is g prime when x equals 1.5? What does that mean? Well, what's the slope of the curve, the tangent slope of the curve, when x equals 1.5? So that's the first thing that we've got to do, right? So let's figure out what that is. So let's see, at 1.5. So what I'm going to do is I'm going to go to where the graph is 1.5, make a little tick on that. Whoops. Make a little tick right there. That's 1.5. Then I'm going to go down and look at the curve there at 1.5. So I'll just maybe make a little dot there. So the first thing I need to ask is it differentiable when x equals 1.5? Well, it looks to me like it's continuous there, right? The point discontinuity is at 1 and 2, not at 1.5. So it's a continuous function. It's a smooth curve, so it's definitely differentiable. Okay, so what's the derivative worth then? What's the value of the slope at that point? Can we do an easy slope calculation? I'm pretty sure we can. What's the run for that segment? Because it's a constant slope all the way across, right? So the slope at 1.5 is the same as the slope at 2.5, etc. So it looks like the run is 2, and the rise is -1. So if I want to get the slope at 1.5, I just apply my m equals delta y over delta x, or y2 minus y1 over x2 minus x1. And it looks like the rise is -1, and the run is 2. So it's -1 over 2, or I could have put -0.5. Okay, -0.5. All right, so let's look at number 2 now. So number 2 is quite an interesting question. Number 2 says, let's take a look at this. Number 2 says, what does the formula below measure? So let's look at this formula. So what are some things that we notice about this formula? And so it should say actually, what does this formula measure, and what else do I need? What do I need to calculate? So it says it's a limit as h is approaching 0. So we've done that before. Limit of f at x plus h minus f at x all over h as h approaches 0. That was the derivative at any point x. But now it's not x. It's actually x seems to be worth 3.5 here and here. So it's subtraction on the top. We're dividing by h. Looks to me like a slope calculation of some sign, some type, right? So it does look like slope. So, and I've kind of given it a bit of a hint over here because I put a slope triangle. Let's see if we can figure this out. So we remember that limit as h approaches 0, rise over run, we call it the difference quotient. And so h is the run. So I've got some things down here that we can bring up into the picture. So let's look at, where does h go? Well, it looks like h is the width of that triangle. That's the run. Then it says, if you notice, the limit was always x plus h, and then it was x over here. So what's replacing the x? 3.5. So it looks like we're doing the slope from 3.5 to 3.5 plus h. So I've got 3.5. That's where it seems to start. So, whoops. Uh-oh. Lost my 3.5. That's okay. We can just type in 3.5 right there. So 3.5 there. And then if this is 3.5 and then it goes to the right by h, what does that make this location here? 3.5 plus h, right? 3.5 plus h. So 3.5, h to the right, 3.5 plus h. So those are our x values. What are our y values for the slope here? And by the way, this is a secant, right? Between this point and this point. So we're getting a secant slope here. So let's see. what are the values I can get? So the first one I'm going to grab is, I'll grab this and bring it up here. It looks like, oops, sorry folks, I'm losing my mind here. Here's what we're going to do. We've got G at 3.5 there, and then what we need to do is to grab this one here and to get G at 3.5 plus H, and we're going to bring that up to here. Okay, so now what we've done is we've got the change in X shown on the X-axis, the change in Y shown here, and let's see if this matches our understanding of slope. So G at 3.5 plus H minus G at 3.5. Well, that would be that distance there, right? So that's the rise. And then H is the run. It's definitely a slope. It's a slope of a secant, but we're saying that H is getting close to 0. So this H is shrinking. So the 3.5 plus H, the H is shrinking back slowly, slowly, slowly to get to back to, the H is shrinking to get back to 3.5. Well, as H gets really close to 0, the secant slowly becomes a tangent, right? So what we're really doing, this limit, like this, without the limit, is a secant slope. But as H gets really, really, really close to 0, that secant is becoming a tangent. So this approximates the tangent slope if H is really small. So that's a lot of talking to recognize that, oh, this just says find the slope when x equals 3.5. So I'm going to go over to the graph again. I've got 3.5 right here. I'm going to go up, and I'm going to put a little tick. I should have done that here, I suppose, on the x-axis there, and then I go up and make a little mark there. So to me it looks like it's differentiable there. There's no point discontinuity. There's no discontinuity of any kind. It's a smooth curve. In fact, it's linear. So I can just get the slope of that section. Rise is 1 and the run is 1. Oh, so if the rise is 1 and the run is 1, 1 over 1 is 1. So the slope is 1. So that's this formula right here. All it's asking for is, what is the slope when x equals 3.5? What is the tangent slope when x equals 3.5? That's what this means. And you need to be able to interpret that notation as the derivative or the tangent slope. Okay, let's look at our last question. So our last question is this one here. So if h of x equals, whoa, wrong one. If h of x equals negative x squared plus 9, determine the limit as x approaches negative 3 of h of x over g of x. So one of the things that we study a lot in calculus is indeterminate limits, and they occur when you get 0 over 0. So let's just double check and see if we get 0 over 0. Okay, so that's the first thing I would always check for on a limit that has a fraction, right? So let's sub in negative 3, and let's start, the top is h of x, when h of x is right here. So let's see, here's our calculation here. Now, can you see the mistake that I made? This number here should be negative 3. We're substituting in negative 3. So I'm going to replace this x right here with negative 3. So I get the negative, and then brackets, negative 3 squared. What's that? Negative 3 squared, negative 3 times negative 3. That's 9. So negative 9 here plus 9 is 0. So the top is 0. We've got an indeterminate limit. Now, if this was a number like 5, then we would know we're at an x-intercept, and the value would be 5, right? Sorry, it'd be 0, sorry. The y value would be 0. Now, what about this g of x? How do I get that value? Well, g of x is the graph right here, right? So I've got to go where x, I've got to approach x equals negative 3. Well, there's negative 3 there. And it looks as though g of x is, actually, the y value g of x is worth 0. It's on the x-intercept. So this, in fact, is an indeterminate limit. It is 0 over 0. So when we have limits that are of the form 0 over 0, one of the strategies we can use is L'Hopital's rule. Okay, L'Hopital's rule just says that the limit value is the ratio of the slopes at the point of indeterminacy. Okay, the ratio of the slopes at the point of indeterminacy. So, pretty easy to figure out. So that formula is right there. H prime of x divided by g prime of x. Well, what's h prime of x? I think that's really easy to figure out. Negative x squared plus 9. So it's negative 2x. Then I've got to get the slope when x equals negative 3? Well, up here when x equals negative 3, I can see that it's differentiable because it's a smooth curve again, and there's no point discontinuity or anything. It's continuous. So now it's linear, so I just have to do rise over run. Well, what's the rise? 1, 2, 3, 4 boxes, so it's negative 4 is the rise, and the run is 2. 2 goes into negative 4, negative 2 times. So the slope at x equals negative 3 for g of x is negative 2. Negative 2 divided by negative 2 is 1, and so I've just got x left. So all I have to do now is let x be negative 3 because I've gotten rid of that indeterminacy. So there's no 0 divided by 0 anymore. So I just substitute in x. X is negative 3. So that limit is negative 3. So in other words, when I take h of x and I divide by g of x, there's a point discontinuity when x equals negative 3. The y value is also negative 3. Okay, so it actually, the function, when I divide the two of them, it's right there. Right, so there's a hole there, and then the curve, when I'm dividing the curve, does something else. All right, so those are your 3 problems. Hopefully that helps. Make sure when you go through these questions, these graphical derivatives will just be sort of intermixed. Good luck.